Modern carrier networks function as a massive digital nervous system, where every router must execute millions of simultaneous tasks per second to maintain stability. These tasks fall into three distinct categories: calculating complex routing protocols, managing physical hardware interfaces, and forwarding raw data packets toward their destination. Legacy network operating systems often utilize a monolithic architecture, where these different tasks share a single common memory space. In this shared environment, a minor software bug in one background process can lead to a fatal memory overlap. A malfunction in a secondary task can corrupt the memory of a primary one, triggering a total system crash. Junos OS prevents these catastrophic failures through two specific architectural layers: strict physical hardware separation and a modular software design. High availability results from an architecture that assumes software errors are inevitable and focuses on containing them safely within their own boundaries. This diagram illustrates the primary division of labor inside a Juniper router. The hardware is physically split into two components: the routing engine and the packet forwarding engine. The packet forwarding engine, or PFE, is the central element of the forwarding plane. Its singular responsibility is handling the high-speed flow of transit data packets entering and exiting the physical interfaces. As data transits the device, the PFE applies stateless firewall filters and executes routing policies to determine the next hop forwarding action for every packet. The routing engine, or RE, handles the control plane. It manages the system, monitors hardware health, and processes incoming routing protocol updates from the rest of the network. After the RE calculates the active routes, it pushes a master forwarding table down to the PFE, ensuring the hardware knows exactly where to send traffic. The PFE never processes routing protocol updates itself. These are directed straight to the routing engine. Offloading control logic to the routing engine ensures the PFE can maintain high-throughput packet forwarding even while the router is performing massive global routing recalculations. While hardware separation protects the planes of operation, we must look at the software architecture running inside the routing engine itself to see the next layer of defense. This diagram shows the software layers of the RE. At the base is the Junos OS kernel, a Unix-like infrastructure that manages every software process. Junos OS avoids the risks of monolithic design by running every distinct function, from routing protocols to management tools, as an independent module. These modules run in protected memory spaces. Every process is confined to its own isolated silo. The kernel coordinates communication between these silos. Processes can exchange data through the kernel, but they remain logically separated. This isolation ensures that a software module cannot access or overwrite the memory allocated to another process. The physical barriers of the hardware are mirrored by these logical barriers in the software, creating a highly stable operating environment. To see this in practice, we can map the specific Junos OS Daemons, the background processes, directly into this modular architecture. The first column represents the routing protocol process, or RPD. This daemon manages the routing tables and controls the operation of protocols like OSPF and BGP in its own space. In the next silo, the chassis process, chassis-D, detects hardware on the system and manages the properties of the device, including system alarms. The interface process, DCD, defines the physical characteristics of links, such as encapsulation and keep-alive timers, within its own isolated memory. The management process, MGD, provides the interface to the configuration database and handles communication for the CLI. This official documentation lists dozens of other specialized processes, from SNMP monitoring to SDK services, each running as an independent application. This breakdown ensures that every critical router function operates as an independent silo, eliminating single points of software failure. If a software bug occurs within one of these secondary processes, the architecture contains the failure to that specific node. The Junos OS Watchdog timer process constantly monitors these modules. If a process becomes unresponsive or encounters a problem, the Watchdog detects it immediately. As the diagram shows, the failing process can be restarted independently. The adjacent routing protocol processes and the packet forwarding plane remain active and unaffected. This specific module can reboot and recover its state without dropping a single transit packet or interrupting the router's core routing calculations. During this event, the system saves the failure data into a compressed core dump file, preserving the configuration and logs for debugging. Engineers can locate these logs in the /var/temp or /var/crash directories, where files are saved with the format processname.core.corenumber.tgz. This dual-layered defense, hardware separation and kernel-level memory isolation, creates a system where errors are prevented from cascading. True enterprise uptime results from an operating system designed to mathematically isolate failure, ensuring that even when a process fails, the network never stops moving.